Okay, let's get started. Welcome to the Lab 8. Today we're going to talk about the basis vectors, the dimension, and coordinates. And in the second part, it's about eigenvector and eigenvalues. So first, we're going to review the definition of basis vectors and the dimension. The definition is, suppose that V is a subspace of the n-dimensional real space. So the basis for V will be like a set of k vectors if those two conditions is met. The first one is the set of those k vectors is linearly independent. And the second one is the span of this set of vectors is a whole subspace. The second one, which means any vector in this subspace V can be expressed as a linear combination of those bases. So we call the K is the dimension of this subspace V. It is also the number of the basis vectors in this set. So we can show an example of the two-dimensional real space. We have the natural basis vector defined as E1 and E2. So first, we're going to check the set of those two vectors is linearly independent. Here we have a function from Lab 6 to show the vectors of a matrix is linearly independent by using the determinant. So we can check around this cell. We can see those two vectors are actually linearly independent. And for the second one, we can see actually for any vector in this two-dimensional real space can be written as a linear combination of E1 and E2. Because the X defined as X1 and X2, it can actually be expressed as this. X1 times E1 plus X2 times E2. So we can see the span of E1 and E2 is actually the two-dimensional real space. So from those two conditions, we can know that those two is a basis for the two-dimensional real space. So we covered about the basis vector and the dimension. Let's talk about the coordinates. So coordinates is a concept associated to the basis. So suppose we have a set of bases V1 to Vk for the subspace V. So we know for each X belongs to this subspace, it can be expressed as a linear combination of the basis vectors. And it is also uniquely linear combination of those basis vectors. Then we can say the X can equals the A1 times V1 and multiply until the AK plus the multiplied by the VK. So those V1 and VK are the basics. We can stack the coefficients here, A1 to AK. Then this vector is we call the coordinates of X associated with that basis. So the coordinates is only defined when you have a defined basis. Also the same example above, we can say for the X equals X1 and X2, the coordinate is actually just the X1 and X2. But it's a special case. If the basis is not the natural basis, it will not be just x1 and x2. So we can visualize this basis and coordinates by plot them. So here is a function we call plot with basis. It's for two-dimensional real space, and you give the input are v1 and v2 is a set of bases for this real space. Then you give a vector v. It will plot the vector v. Okay, so we can run this cell first, and let's see the first example. The first example, we plot the natural basis E1 and E2. And we plot the vector V using on those bases. So let's run this. It is slow on the first time you run that. So here, we can see the blue arrow is the E1, and the green one is E2. The first plot shows the bases. First, we can see those bases are orthogonal, and they have and the norm is 1, so that's a natural basis. And then in the second plot, the red point is a vector v we provide for this function. It's 3 and 2, and we can see the 3 is the coordinate for the first basis E1, and 2 is the coordinate for E2. Yeah, is there any questions so far? So we can also plot this using a different set of bases. For example, here, the next example, we are not using the natural basis. We use the V1 and V2 here. And we still plot the vector V with the 3 and 2 as its coordinates. So I can see here, the basis is different from the natural basis, but it can still be the basis for this subspace. And we can also express the vector V using those bases. So here, the V equals 3 and 2, which means the V equals 3 times V1 plus the 2 times V2. So this 3 and 2 are the coordinates on those new set of bases. Okay. Okay, next is you're asked to plot the vector V using another set of bases. V1 equals E1 and V2 equals 2 times E2. Yeah, we'll give like 1 minute for this. Yeah, so, because this is very simple, we just go through together. We can write the E1 equals E1, or we can just directly see 1, 2, or 1, 0. And the V2 equals 0, 2. It's the same thing. Then we use this function plot with basis. Okay, is this the same as your plot? Yeah, so we can say for those bases, the difference is the norm is not equals 1. For example, the V2, the norm of the V2 is not equals 1, but it is also a basis. Okay. Any questions about the basis vector and the coordinates?
Yeah, that's good. I'll just add some comments. If you go back to the definition of basis vectors, Lou.
Okay.
So I don't know if this is a culturally appropriate reference, but you guys, most people learned the story of Goldilocks and the 3 bears. Okay, so the porridge is too hot, the porridge is too cold, the porridge is just right, okay? So I say a basis is a Goldilocks notion. Why is that? Well, if you have too many vectors up there, they cannot be linearly independent. Okay, so you have to have you can't have too many. Otherwise, you throw in one more, it becomes dependent. Okay, and the span has to generate every vector in the set. So there has to be enough of them. Okay, you can't have too many, you can't have too few. So that's sort of like the porridge too hot, the porridge too cold, the porridge just right. The right number of vectors, that's what a basis is. Okay, so you can write every vector in the set as a linear combination of those, and you cannot do it with fewer vectors, okay? And you can't do it uniquely if you add more. So that's my mental way of keeping the notion right. And so bases are how you generate vectors. We do linear algebra in vector spaces, but I don't know how to put a vector space into a computer. But I can work with the basis vectors, just like we were calculating the null space of a matrix with the command in Julia, and it returned this orthonormal set of vectors whose span was the null space. Yes?
So does the amount of vectors in the basis vector, if you're working in Rn, does that mean you need vectors for basis?
So the question was, how do you kind of get the number of these things? Yes, so if V was the entire space Rn, so it's not really very much a sub, but it's, it is, Rn is contained in itself, then you would need n vectors. But if say n is 3, something we can picture, and you have a plane that goes through the origin, okay, so then it's a subspace. Then you need 2 vectors in there. But if you chose 3 vectors from that plane, they would have to be dependent. Okay, so draw yourself a plane in R2, a plane, and try to get 3 independent vectors that lie in the plane. You'll find that you cannot do it, okay? Now in R3, you can choose 3 independent vectors. Here's E1, E2, E3, but they don't lie in a plane. They generate all of R3. So that's why it's just enough to be independent and enough to generate all of the vectors in the set. Because in the plane, I could have just 1 vector that's non-zero and it would be linearly independent, no problem. But I can't generate all of the vectors in the plane with just 1 vector, I need 2. Okay, the question is, if I'm once again, like the top of this desk is R2, can I do three different vectors that no one is parallel to the other, can they be linearly independent? And the answer is no. They can all be written as a linear combination of E1 and E2. So they can all be generated from two vectors, and that tells you the three cannot be linearly independent. So it takes a while to get that into your head, but that's what, not too many, so I can't put three vectors in a plane. I can generate every vector in the plane using this vector, and this vector. It's true, I can generate everything in the plane, but they are not independent, so I really have extra vectors. That usually causes problems. You want the minimum set. One vector in the plane, non-zero, would be linearly independent, but I can't generate all of the vectors in the plane with just going on a line. I need at least two. Okay, so that's how I remember the idea of generators, the minimum number of generators to get everything in the set. And so that's why I call it a Goldilocks condition. Does that help, or does that just screw you guys up? Sometimes mnemonics are good. Anyway, thanks, Lou. Why don't you go on to the next part? Then?
Okay, thank you, Jesse. Okay, the problem 2 is about rank. So the rank of a matrix A is the dimension of the vector space spanned by its columns. So you can see it has the column vectors, and those vectors can span a space. The dimension of this space is the rank of the matrix. In Julia, we can use the rank function to calculate the rank of a matrix A. And we can also use the Grant-Smith function we learned earlier to obtain the basis of its column span. So here we give the Grant-Smith function from Lab 7, which also, I think this one excludes the dependent vectors. Okay, so here is the example. We give a matrix A, which is a 2 by 4 matrix, and we can calculate the rank of this matrix, which is the dimension of the column span. And we can use Grant-Smith to obtain a basis. The basis is for the vector span, or the column span of the matrix A. So because this rank is the dimension of this column span, so it will be, we can see if this is the same. You can see the rank is 1. Also, from the Grant-Smith function, we get just one column vector. So the set of bases here is 1, which is the number of the dimension is also 1. So we can illustrate this. For example, we can see each column of this matrix A can be written as a linear combination of these bases. So here the basis right now is just one. It's just one vector. So we extract this vector to a vector V. Then there's a for loop goes through all the column of this matrix A. And we can actually calculate the coordinate. Here the coordinate is C because the basis times the coordinate A, which will equal the column of this matrix A. So we can solve this equation by using the pseudo inverse here to get this coordinate. And then here we show the coordinate is, the basis multiplies the coordinate is actually equals the column of A. I think here because the V, the coordinate is just a scalar, so we can write this before V, but usually the coordinate we will write after the basis. So yeah, we can see here, for the first column, the coordinate is 1.4-ish, and the norm of the subtract AI of this is equals 0. So basically, this shows that the V is actually the basis of its column span, and which means each column of this matrix A can be written using those bases, and there's a coordinate exists. Yeah, so here's an exercise. We give the 4 vectors here with a column vector, and compute the dimension of this span of these vectors. And also compute the basis of this vector, the column span. Yeah, we'll give a couple minutes for this. So first, for the dimension, we want to use the rank function. So we're gonna make the matrix A using those columns. Then the dimension will equal the rank of this A matrix. And the same thing, we use the Grant-Smith to get the basis. Okay, so we call it. Okay. Okay. Is this clear? And the next exercise is just want to show if you change the order of these vectors, you will get a different basis. But the dimension will be the same. So here we can change the A matrix. Probably we use V2, V3, V4, and V1. We can see the dimension of this column span will be the same, but the basis will be different. Yeah, we can see this basis 2 is not the same as the basis. Yeah. Is there any questions so far? Okay.
So let's just look really quickly at the friendly tests. So notice that, okay, here's A, and then we threw all the basis vectors in, and if the ranks are still equal, it means the number of linearly independent vectors here are the same as the number of linearly independent vectors there. So what that's doing is saying the basis vectors didn't add anything, but you could have added 0 in there. If you wanted to be even more sure, what you would have checked is that this rank is also equal to, and I should have done this. This would be T3, and say, don't need the brackets. Okay, so now it's saying the number of linearly independent vectors here is the same as here, so I have enough vectors here to generate everything in V1, V2, V3, V4. So that's asserting the spanning condition, and et cetera. So you can use the rank to just check the number of linearly independent vectors in a set. So, and what the rank command is really doing, it's forming A transpose A and doing LDLT and looking at the number of non-zero elements on the diagonal of D. Bingo. We're going to skip all the way down to eigenvectors and eigenvalues, because I think you guys can play with the, you can play with null space and things like that on your own. So let's do this thing, which is a little bit harder property of a matrix. So fortunately, there's this always a very nice command, whether it's in MATLAB or Julia. In MATLAB, it's just EIG, eig. In Julia, it's eigen. So eigen is a German word that means self. And the reason it comes in self is a vector V, a non-zero vector V is an eigenvector of A. If you multiply A times the matrix, so A has n squared entries. N elements in this row, n elements in this row, n elements in this row, and n rows. And it's multiplying a vector with n elements in it, okay? So to just get out that is just the same thing as multiplying the vector by a scalar seems like it's impossible that could even happen, okay? I can take 3 times a vector and get this 3 times a vector a scalar, but to take n squared numbers, multiply them times a vector, and all I get is taking that vector and scaling it by a single number seems really, 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 really weird and almost impossibly special. Well, it turns out if you allow the lambda, it's called an eigenvalue, V is called an eigenvector, self-vectors and self-value. So matrix times a vector is the same as a scalar times the vector. If you allow lambdas to be complex numbers and V to have complex entries in them, then all matrices have eigenvalues and eigenvectors. So you can prove that. It's in the appendix of the book if you want to go through and see where the theory comes from. On our first introduction to these, we want to keep it simpler. And so there's a really nice fact. If a matrix is symmetric, so like A transpose times A is symmetric, or we could put A plus A transpose, that would be symmetric as well. Real symmetric matrices always have real eigenvectors and real eigenvalues. So symmetry, this kind of weird property we talked about, matrices that when you transpose them, you get the matrix back, that's reflected kind of bizarrely in this eigenvector property where the eigenvalues are real numbers and the vectors are real vectors. They don't have to be complex vectors and complex values. In the homework, I have you take a 3x3 matrix, and we're going to estimate the probability that a 3x3 matrix always has at least one complex eigenvalue, okay? So we'll do non-symmetric matrices, and you'll see how that works out, and you realize, yes, we really should allow complex numbers. You've done complex numbers when you did the quadratic formula in high school. Okay, so you're okay with I or J, whatever you want to label it. If you're an electrical engineer, I is for current, and so we let J be square root of -1. That's the weird thing electrical engineers do. All the rest of the engineers call, and the mathematicians call square root of -1 I. And in Julia, it's I as well. So here, we're just going to use the random command, generate a random matrix. We're going to turn it into a symmetric matrix by doing A transpose A, and we calculate E equals eigen. And it's sort of like the LQ command. We can pick off the P, we can pick off the L, we can pick off the U, etc. The way Julia works, we get this as a structure, and we do E dot values, and we get the eigenvalues. And we do E dot vectors, and we get the eigenvectors. So what this means is A multiplied by this column vector will be equal to 0.0628 blah, blah, blah times the vector. A times the second column vector will be 0.6813 times that column vector. A times the third vector in here will be 2.97 times the vector. And A times this vector will be 4.483, etc. So AV equals lambda V. If the magnitude of lambda is less than 1, it's shrinking the length of the vector. If the absolute value of lambda is 1, the length of the vector is not changing. And if the magnitude of lambda is bigger than 1, it's amplifying the vector. Does that make sense? A times V is lambda times V. You know, it could be minus. That just flips the direction, but it still scales it by the number, okay? So a minus sign, instead of the vector pointing this way, you multiply by A, it's the same vector pointing backwards, and then you have the scale. So that's kind of amazing, okay? So where do engineers use these eigenvectors? We're going to look at dynamical models a little bit in this course in Project 3. And so X is a vector that'll have positions and velocities, and it could have angles, it could have momentum, it could be electrical circuit, it's currents and voltages. But these are physical quantities in your model of your system, and you want to know how those quantities evolve over time. And if the system is linear, the value of the positions and velocities at time k plus 1 may be just a matrix times the values of the state of the system, the positions, velocities, currents, voltages at time k. So this is called a discrete times linear system, and linear because it's a times x, not a times x squared with sines and cosines. Okay? So now we notice these eigenvalues. We have 2 of them in magnitude less than 1 and 2 of them with magnitude greater than 1. So what we're going to do is take the initial condition on this system. We're going to start the system on an eigenvector. A times the eigenvector is going to give us lambda times the eigenvector. If we multiply by A again, we get A times lambda times the eigenvector, which is lambda squared times the vector. We multiply again, we get A times lambda squared times the vector, which is lambda cubed times the vector, and you can see how this just iterates. And so if lambda is smaller than 1, it's going to crush down, and if lambda is bigger than 1, it's going to blow up. And so we're just going to see how we can understand the dynamics of this system. So it started on the eigenvector 1. The vector gets multiplied by something far less than 1. Boom, that's 0.06 of the vector in terms of the magnitude is what we're plotting here. So this is k, the iterate, and norm of x, the size of the vector. And so that's the length of the eigenvector. Julia gives us normalized vectors. They have length 1. And then that's 0.06. 0.06 times this is 0.06 squared, which is really tiny. And then, so it just decays. Here, I changed it to 5 instead of 10 because it blows up so fast. Okay, so this is the third eigenvector. We don't care about these numbers so much as we care about this. This is the amplification factor. So let's call it 3. 2.97, that's 3 for an engineer. So each time we go through the loop, we're multiplying the vector by A. It's the same thing as multiplying by the eigenvalue. So we have 3 times x, 3 squared, which is 9 times x, 3 cubed times x, which is 27, 3 to the 4th, which is 81, 3 to the 5th, etc. And so notice how the solution, which is the norm of the solution we're plotting here, just blows up. So how the dynamics behave on a vector, individual vectors, when they're eigenvectors, is really easy. They just get multiplied by numbers. Now, if the eigenvectors form a basis, how can you analyze what a general vector is doing? Okay? How can you analyze what a general vector is doing when a matrix multiplies it? Well, write your vector as a linear combination of the eigenvectors. That's what bases are for. Do A times your vector, you've got a coefficient times A times the first eigenvector. That's just lambda 1 times the eigenvector. A times the next one, you've got a coefficient in front, and you've got lambda times that vector. If that eigenvalue is bigger than 1, you're blowing up in that component, and if it's less than 1, it's crushing down. You go A times the next eigenvector, it's the eigenvalue times it. So you can decompose what a matrix is doing into the directions determined by the eigenvectors. That's amazing, okay? N squared elements, if instead of looking at the vector in E1, E2, E3, E4, I look at it in the coordinates coming from the eigenvectors, I can look at each A acting on it as A acting in this direction, A acting in this direction, A acting in this direction, and each one of those directions, A is just multiplying the vector by a constant. And so if I iterate my matrix, I can see the directions in which things are crushing down, and I can see the directions in which it is blowing up. Okay, so we did that one. So here's my question. What will happen when the initial condition is 2 times the first eigenvector plus 3 times the third eigenvector? I'm going to iterate, okay? To answer it, you need to go back and look at, we don't care what the vectors are. You can check, they're linearly independent. But it was 2 times the first eigenvector and 3 times the what did I even say here? 2 times the first one and 3 times the third one, okay? So here's the first eigenvalue. Here's the third eigenvalue. So what's going to happen to the linear combination 2 times V1 plus 3 times V3 when I iterate it through the matrix? What's going to happen? Will it stay bounded? Will it shrink? Will it stay constant? Well, we can use linearity. We know our vector is 2 times this plus 3 times this. A times this component is going to shrink by it's multiplied by 0.06. A times this component gets multiplied by 3. I apply A again, this component stays multiplied by 0.06, so now it's 0.06 squared, and this component is 3 squared. So we start out with something in a plane, and we keep applying A, it's going to crush down on the values that are less than 1 and blow up along the direction where the eigenvalues are bigger than 1 in magnitude. So that's the power of linear algebra. And so we can just run this and see. And yep, it blows up, and it's because this eigenvector, when I iterate through my system, it just disappears. And this one gets amplified every time I go through by a value bigger than 1. And if I take anything bigger than 1 and I keep raising it to a sufficiently large power, in magnitude, it just goes off to infinity. So that's what's summarized here, is how you can use eigenvalues and eigenvectors to understand how matrices operate on an arbitrary vector. You simply express the vector in the coordinates given by the basis of eigenvectors, and then when you apply A to it, you see exactly what's happening. It's only multiplication by scalar, a different scalar along each direction, but each of those directions is just multiplication by a scalar. Now, if you have a segue that you're riding and you go over a bump in the road, which is called a perturbation, what do you want to happen to that perturbation? That it causes an amplifying wave in your system, or that perturbation goes bump, and then when the dynamics happen, it crushes out and you just go back to your normal speed? The latter is what you want, okay? You're riding upright, you hit a little bump, you don't want the Segway to do a face plant. So this is where stability of dynamical systems comes from. So if you go off and take a feedback control class, it's really when the system is linear, the magnitude of the eigenvalues tell you what's going to happen when the system is confronted with external energy. Will it dissipate it? Will it dissipate it, which is what's happening here in a very fast way? Will it amplify it? And that's when you do the face plant. Okay, so this is just giving you a hint of why eigenvalues and eigenvectors are important. Okay, so this is just the part in the book that says if you write a general vector as a linear combination of eigenvectors, you multiply the matrix times that. It's just multiplying the individual components by the eigenvalues, and if you square it, you're just getting the square of the eigenvalues, and in general, a to power k. It's just each of the matrix on this is just acting on the individual components in the eigenbasis. And so what I want you to do at home is take this example. So here's another symmetric matrix, A plus A transpose. It has real eigenvalues, -4, let's say, -0.5, 0.1, and 1.5. Okay? Give me the subspace of initial conditions such that for all of those initial conditions, when I let my dynamical system evolve, the solution stays bounded. It doesn't blow up. Okay? What's the set of all initial conditions? And what you know is you have 4 vectors. That's a basis for R4. Any vector with a component along this one gets amplified. Any vector with a component along this one gets crushed by 0.6. And 0.6 to power 10 is really small. Any vector with a component along this one gets crushed by 0.1, 0.1 squared, and any vector with a component along that direction gets amplified by 1.5 each time it goes through the system. So tell me, what is the set of all initial conditions that would give rise to a bounded solution? Okay, so write your vectors, and then you can check it here, and you'll see that the assertion test doesn't tell you which vectors it is, because we just calculated some vectors that are orthogonal to those, and we just checked that you've got two vectors that are orthogonal to them. And so if you return 0, 0, then you will pass this test. But that's why it says all nothings means likely correct. It doesn't mean you're actually correct, okay? So if you just cheated and said V1 is 0 and V2 is 0, you would definitely pass the friendly self-test. So with that, I think we need to stop so Tribby can get set up. But the key thing of bases, they give you coordinates often in which a problem can be very hard to understand in the natural basis, but if you go to the basis of eigenvectors, and you're trying to understand what happens when you iterate a matrix successively on the vector, it becomes transparent what's happening in this basis because each component is just being multiplied by a scalar, and that's amazing, totally amazing that that's even possible, okay? So that's my story, and I'm sticking to it. So, Tribby, thank you. Question? Amazement? Ooh, ah. Okay, so that's what the... And the faculty in computer science who teach machine learning and computer vision wanted to make sure that you guys had some exposure to eigenvalues and eigenvectors. So this will help you if you get into those two. EECS 445, I believe that's the machine learning course, and 442 is the computer vision course. But I think once you've had Rob 101 and you've had 280 and 281, you're actually ready for those 400 level courses.
So we're going to take over from where we left last time. We were still kind of going over vector spaces, and we talked about subspaces, we talked about span, we talked a little bit about basis vectors. I'll go over it again just because it's on homework. And then we kind of went into null spaces. I don't think you guys had range before this week, so we're going to go into that and the rank nullity theorem. And then finally, for the Julia part, we're going to take over, like Eva's going to go over the mobile robot example from the book, which is modified in the homework, but we're going to go over the original example that you see in the book, and hopefully that translates into what's on the homework. All right, so we left off with null spaces, and we said that for any matrix A, we can define two subspaces that are special and follow a special property, which are null spaces and the range of a matrix A. Null space is simply all the set of vectors x in Rm, I'm missing the R there, such that Ax equals the 0 vector, right? And the range of A, on the other hand, is defined as all y's such that it contains the linear combination of the matrix A with any vector x existing in m dimensions. So basically, range can be thought of as it's just the column span of A, right? because the column span is if x is m vector, if x is of length m, then the column span of A would be each mth column of A multiplied with x, and that gives you the range vector. Right? This was clear? And then from there, we talked about why null spaces are important for existence and uniqueness of solution. And then we talked about the basis vector. So the set basis vectors should follow these two properties. One is that they should be linearly independent, and two, that the span of them should cover every element in any set V that V1 to Vk is a basis of. And now I think in lab you guys talked about how eigenvectors are basis vectors, right? Because they follow those two properties. I'm trying to look for, okay. So for range, we said a range was a column span of a matrix. And we also talked about column span as a definition as column span of any matrix is just the span of all the columns, right? And we said that range of a matrix is a subspace. And last time we talked about how column span of a matrix will be a subspace, or in general, span of any set of vectors is going to be a subspace, right? Yeah? Okay, and then from there, I think this week we defined rank of a matrix and then the nullity of a matrix, right? So simply put, rank of a matrix is just the dimension of the column span of A. Do we understand what we mean by a dimension? Dimension of a matrix or of a subspace? So this is related to like the concept of basis, right? So if the dimension of any subspace is the number of linearly independent vectors that can exist in that subspace or in that vector space, right? So for any matrix A, the dimension would be the number of linearly independent columns or rows, whichever is greater in the matrix A. Yeah?
We also say that the dimension of a matrix also be number of basis vectors instead of basis vectors?
Yes. So the other definition that was brought forward was that can we say that the dimension of a matrix is also the number of basis vectors in that subspace or in that matrix, right? And then nullity is similarly, so then rank then becomes the dimension of the subspace, which is the column span of A. So we have a set of all the columns, all the spans of A that can exist, which is the column span of A. And the dimension of that would be the rank of the matrix. So that basically means the number of linearly independent columns of A will be the same if A is all linearly independent columns, right? The dimension of the column span of A, what would that be? A is invertible, so all the columns of A are linearly independent. What is the rank of A? Yes? Yep, the number of columns of A, right? So can I also say that it is the same as the dimension of the column span of A? Right? Yeah? And what would be the nullity of that matrix A? 0. Yep. Or actually, yeah. And then by that logic, if you remember, we talk about the rank nullity theorem, where we say that any matrix A can be defined, so the dimension of any matrix. So rank nullity theorem is basically the dimension of any matrix A is equal to the rank of the matrix A plus the nullity of the matrix A. Does that make sense? And I think in your Julia homework, they have you calculate the null space of A, the column span of A, like the range of A, that is, and you prove the rank nullity theorem. Are there any issues on that side of the work, or is the math of it clear? Yeah, that part's easy. And then the last thing, I think, there's also span, but we talked about it, basis vector, we talked about it. So the last thing on the homework that I think is new is eigenvalues and eigenvectors. I think you might have just gone over these, but as a refresher, eigenvalues and eigenvectors, they're these, the eigenvalues are these special values such that A times V is lambda V. So this would be the most generic thing you want to remember, where V would be your eigenvectors and then lambda would be the corresponding eigenvalues. And then different things happen when lambda is discrete, and then there's also properties of, like we were talking about, symmetric matrices. They always have real eigenvalues, and there's good amount of work on different properties of them, but I don't think that's relevant to what we're doing. I think we just teach you here how to calculate and how to use eigenvalues and eigenvectors, so we're going to stick to that discussion. But if you look up online, or maybe even in the book, you can see the different values, the different properties of eigenvalues and eigenvectors. And then in your homework, we give you a matrix A, and we have you find the eigenvalues and eigenvectors. And then the formula to do that is right here, because the property that we're satisfying is AV is equals lambda V. We can take out lambda I from here and bring it to the left-hand side, which gives us this equation, lambda I minus A times V equals 0. And then to calculate the scalar lambda, we notice that the determinant of the left-hand side equal, if you put that equal to 0 and you find out the lambda, those are your eigen values. Right? Yeah.
Why did you multiply lambda by the identity matrix?
So
Does that make it just a matrix that has that lambda value on the diagonal?
So compare the left and the right-hand side. So A times V will belong in Rn, right? And if I were to bring it, and then A is M cross N. So for this expression to make sense, A here will be N cross N, it's a square matrix, right? And for this expression here to make sense, you have to have something like lambda. So what I'm trying to do is I'm trying to put lambda, oh shit. And then zeros, so on, n times to lambda, lambda, lambda. And that's when the matrix multiplication would make sense.
So is that just like essentially put lambda in a matrix form so that you can work with it today?
Mm-hmm. Yep. You bring it on the other side, and then you put the determinant. And then for eigenvectors, we can calculate this equation right here. And that's basically like solving this is same as solving that because it's a zero vector, right? That's pretty much it. If you have questions, come to either office hours, we can go over the recap again, or if you want, we can go over the project 2 least squares pipeline. I have an example on that if we have time. Otherwise, I think it'll be helpful if we go over the example from the book, because it's on the homework and it's in the optional read, so I don't expect you guys to have gone over it.
All righty. Are we ready? Perfect. So we are going to go over the steering mobile robot example that's in the book. So that's in section 9.10, page 178 of the book. If y'all want to pull that up, but you don't have to because it's here already anyways. And the purpose of that example is to essentially show you all how we can apply how underdetermined equations show up in robotics. And so, are there any questions so far? Or I'll just go ahead and get started then. Cool. So in that example, we're given a robot that kind of looks like a Roomba, I guess, which is a vacuum robot. And we're told that this robot moves in 2 directions, so the X and the Y direction. So it lives in a 2D plane. And so we're given that we can denote the position of the robot at time k as pkx and pky. So we can put that in a vector form. And so what that means is that, for instance, if I want to find out what my position at the initial time, that would be p0. So that would look as p0 is equal to maybe 0, 0 if the robot starts at the origin, right? If the robot ends at the origin, and let's say that that's at maybe 20 steps into the future, that would be p20, and that would be p20 is equal to 0, 0. Does that make sense? Cool, awesome. And so what we have next is this random equation over here. I'm just gonna switch over here. And so we are told that that did not work. Did that work? Okay, cool, awesome. And so we're told that, let me just write it down, that given the current position of the robot pk and this uk, I can tell you where the robot will be in the next step, right? And so this is essentially what is called the equations of motion, or the dynamics of the robot. And you don't have to worry too much about where this equation comes from, what the A and B matrices are. We'll go over all of that in project 3. Right now, all you need to know is that we have this equation, and because of this equation, we are able to predict what the robot is going to be doing. So question is, what is UK? Well, UK is the control input that's, that the robot is given. And you can think about this as the motor torques that are coming from the motors, or maybe an external force, like, I don't know, maybe you're mean to the robot and you decide to kick the robot just for fun, which I definitely don't do that. I mean, I guess we do that for experiment purposes, but that's what UK is. It's just an external force, and essentially what we're doing here is, given this force, UK, and our kth position, we want to know what's going to happen at pk plus 1. Any questions so far on that? Cool, awesome. So we're given that well, this is going to take a minute, but we're given that the dynamics of our robot, that the A matrix is this, for this particular robot. Again, don't worry about where this comes from, it's just given right now. And that our B matrix is that. Now, you may have noticed that rather than, I haven't really talked about time or anything of that sort, right? And so what happens is that even though the equations of motions are actually continuous through time. When we're working with computers, in order to make the math a lot easier, we discretize it. Now, what does that mean? That means that, again, I'm going to switch to this. It's going to take a minute to come. Cool. But let's say that I have, this is time, this is like maybe my position in the X, right? And maybe my robot is doing something like this, right? In order to work with computers, what we do is that we discretize time, and that means that I'm just going to choose certain intervals to look at my thing. So maybe this, we call this here, we call this delta t. And so I will only observe what my robot is doing at delta t. And that just makes life easier in terms of calculations. Again, don't worry too much about this. We will cover this again in Project 3. This is just so, you know, the homework problem makes a little bit more sense as to what's going on there. Continuing on. And so what this means, once this thing pops up for the people on Zoom, so this means that if I am at time tk, I can calculate that in terms of intervals by getting my number of intervals multiplied by delta t, and that will tell me what time I'm at, right? Any questions so far? Cool, awesome. So we now have this equation, apk plus buk is going to give us pk plus 1. Now, what if I tell you that if you give me your initial position, the robot's initial position, and a control sequence, right, u0, u1, u2, u3, I can tell you where the robot will be in n steps. That's pretty useful, right? And so that's what this equation allows us to do. So given P0, which is your initial condition, I can define what my P1 is, right? So I know that my P1 is equal to AP0 plus BU0, given this equation up here. I know that my P2, again, is equal to AP1 plus BU1. But guess what? We just defined what P1 is. So I can just substitute that in over here. And now I have an equation that just relies on P0, U0, and U1. And I can do this over and over again up until I get to Pn, where n is my nth time step, right? And I can write down an equation that just depends on P0 and my control sequence, which is U0, U1, up until Un minus 1. Any questions as to where this equation came from? Does this make sense so far? Yeah? Okay, cool. Awesome. So for instance, let's say that we want to figure out the control sequence that gives us the, that gets us from the initial position P0 to the final position Pn. Well, all I have to do is grab this final equation, right? And just do a little bit of rearranging. And so I can do Pn minus bring this term over to the left, and I am left with this equation over here, right? Where what I'm trying to find out is this control sequence. I know this matrix because I know what my A and B matrices are, right? Because that's what's given to me by the dynamic equations that we talked about, right? So I know this term and I know this term. Is this starting to resemble anything that we're familiar with? Yes, question?
You know what n is?
Yes, we know what n is, yes.
What does that represent?
So n represents the time steps into the future that you're trying to predict where your robot is. So, go ahead. Yeah, so for instance, if I tell you that I want to know where my robot is in 2 seconds, so let's go back up here. So n is essentially, I guess you can think of n as k. N is the same thing as k, right? So if I tell you that I want to know where my robot is in 2 seconds, tk is equal to 2. Delta t, that's something that you will be given. So for this particular problem, it's 0.1. So then n would be k, and so then you would do 2 divided by 0.1, and your n would be 20. So 20 time steps into the future is equal to 2 seconds. Does that answer your question? Cool, awesome. Any other questions? Yes?
I'm a little confused by like the A to the N.
Yes.
N minus 1. So isn't A constant?
Yeah, so let me actually derive that here for y'all. So let's just write this down. Cool. Alrighty, did that pop up? Yes, it did. Cool. So we're given that pk plus 1 is equal to a plus pk plus b uk, right? All right, so I'm going to tell you that p0 is going to be, I don't know, pick your favorite number. So for right now, let's just say it's just x and y, or whatever. It doesn't really matter. I can define p1 as a p0 plus b u0. Does this step make sense? This right here? Cool. I know that my p2 is equal to a p1 plus b u1, right? But guess what? I already know what my P1 is, right? So I can say that this is equal to A, substitute what my P1 is here, A P0 plus B U0 plus B U1, right? So in this case, I get A squared P0 plus A B U0 plus B U1, right? So if my N was equal to 2, this is what my equation would be. So A is known to answer your question. The N on top, it just signifies however many powers you're taking, because again, you're replacing your P1 with A P0 plus B U0. You'd be replacing your P2 with that. And so this final equation over there on the right here is just what happens once you do this recursively over and over and over again. Does that answer your question?
Yeah.
Cool. Awesome. Yeah. All righty. Any other? Yes.
Using that equation that you just derived, we also solve like the vectors
Exactly. That's where we're going to go next. Yeah. So the question was, given the equation that we derived, which is this equation right here, right? Can we solve for the control vectors u0, u1, etc.? So yes, that's exactly what the thing is. Yes.
Another important thing to note would be the dimensions. So like A
Yes.
and the B, and then how it will always be, like you can always multiply it. So the dimension of N and S will be compatible.
Exactly. So once we define what M and S are, yeah, you'll notice that, yeah. These dimensions always have to be compatible, and they will always be compatible. Otherwise, you would not be able to do that multiplication. So thank you for bringing that up. Cool. Awesome. So what we're going to do next is we're going to define these S and M matrices that Trivi just brought up. And this is just to make our math equation look a lot nicer and neater, really. So we're going to say that S is equal to A to the N. And we're going to say that our M is equal to this matrix over here that's defined as such. And what that means for us now is that our equation now becomes P of N minus SP0 is equal to M U sequence, where U sequence is U0, U1, dot, 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 etc. So great. We now have our equation. So now let's take a look at the problem. The example in the book is, can we find the control sequence that takes us from P0, where P0 is equal to 1, 1, to the origin, right, 0, 0, in 2 seconds. Again, 2 seconds gives us N is equal to 20, as we talked about. And so I claim this is an underdetermined problem, and I was going to ask why, but the answer is already on there. But the fact that in our control input here, given this particular problem, we have 2 control inputs. So our U matrix is U0 would be in R2. And so because of that, we have 40 unknowns, right? 2 times N, because we have 2 control inputs, so 40 unknowns. And we only have 2 equations. And so therefore, this is an underdetermined problem. Does this make sense? Does it make sense why I said we only have 2 equations? And why I say that we have 40 unknowns? Where are those numbers coming from?
I think if we talk about the dimension of S and then the dimension of N, we can find that out.
So let's go back to the problem. So your dimension of, I guess I'll just go back to B. The dimension of B over here is 2 by 2, which means that the dimension of U, I don't even think that we define what U is here, but I think it's defined in the book. But the dimension of U is 2 by 1, right? The dimension of A, again, is 2 by 2. So yeah, does it make sense now? Why 40 unknowns? So 40 unknowns because, again, we say that we want to find our n is 20. That means that I need to find 20 control sequences to get me there, right? But for each u, I require 2 numbers. So 20 times 2 gives me 40. Again, why is B 2 by 2? Why is A 2 by 2? Why is U 2 by 1? We will talk about where the equations of motions come from. 2 equations, because again, our equation tells us the position of where the robot will be in, and that position is x and y. So we get information about x and y. So we have 2 equations that tell us about x and y. So 2 equations, 40 unknowns. Does that make sense now? I see nods here and there. See a little bit of confused faces. Should I go over it a little bit more, or? Yes, I can write it down. Let me, okay. It takes a minute. Cool. So our A is in 2 by 2. This should still be in 2 by 2. And it's going to be difficult to calculate off the top of my head. Let's see. Do you have the equation for m?
Yeah, it's a n minus 1 times b.
Times a minus 1 times da-da-da. Okay, so m. Etc. B. So this over here, you have 2 by 2, that would give you up until, so it'd be 2 by n minus 1. Does that make sense? Yeah. Does it make sense how I got 2 by, so maybe let me go over this. So your m is a n minus 1 times b, so on and so forth, right? I know that my a is 2 by 2. My b is 2 by 2. When I multiply them together, they'll still give me 2 by 2. I have n minus 1 terms, right? Sorry, n terms. Thank you so much. I have n terms. So what does that mean for the dimension of m? I will let y'all think about that, and I will. Go ahead. N? By what? Yeah, just the total. I see another hand in the back. Yes. Okay. Correct. Does it make sense now? All right.
Shouldn't it be 2 by 2 times n?
2 by 2 times n.
Because AB is n cross n, and there's 2 control inputs.
There is 2 control inputs. Exactly. Good catch. That is correct. Good catch there. Does this make sense? helpful. So again, let me go back here. Yeah, that would have to make sense. So again, you have 40 unknowns, right? Yes, it has to be 40, yeah, because this is going to be 40 by 1, right? Because you have U0, which is 2 by 1, U1, which is 2 by 1, so on and so forth. So this is 40 by 1. We know that this is 2 by 2, so that makes that 2 by 40. Does that make sense? So again, 2 equations, 2 unknowns, so that gives us an underdetermined problem. So the question is, how can we solve underdetermined systems of equations? Any takers? Yes?
We use like what we learned before with like solving the AX equals B.
Yes, exactly. And so what are some ways that we learned of solving AX is equal to B? Yes, go ahead.
Like using taking like the argument and by doing like the A transpose. So I'm trying to remember the exact equation I was going to say. The A transpose times the inverse of A times A transpose times B.
Yes, exactly. Does that make sense? Did you guys hear that? So there are various ways that we can solve for this. We learned about QR factorization, right? That's one way we can do this. You can take the inverse, and while doing that, you can use your LU factorizations and all those different things. So there's multiple ways to do that. So let me throw back the question again at you guys. If we're saying that this is the same as AX is equal to B, what is my A and what is my B in the, I guess, in the underdetermined systems of equation? I'm going to go back over there with a hat.
A would be M, and then B would be Pn minus H P0.
Correct. Yeah, exactly. So this would be my A. This would be my X, right? And this would be my B that I'm solving for. Awesome. So this is exactly what our friend here said. So A transpose A, yeah, that equation over there is what we can use to solve for it. The thing, though, is that we can actually use QR factorization. And when I use QR factorization, I end up getting my Q and my R matrices. And I can solve for my B, or I can solve for my X star using these equations here. If QR factorization doesn't make any sense, let us know, and we can go over it in office hours. But for now, I think I'll power on so we can get to the end of this. Any questions so far? Cool, awesome. So what I chose to do is I chose to, again, use QR factorization as well as forward substitution. So Julia has this really handy function, QR, which can give you your Q and your R matrices. And once you find that, you can get this beta matrix using your forward substitution method. And after that, you can get your X star or your X. Does this make sense? Now, does it make sense why we would choose to minimize U in a practical sense? Like the example that we're working with right now is a robot. Why does it make sense to take the minimum norm of U? Yes, go ahead. You said it makes it easier for the robot too. So you're saying processing speed? Not quite. Any other takers? Why would I minimize the torque? Another way, let me rephrase that question. Why would I minimize the power that the robot requires to use? Yes?
To get like the most efficient use of like the energy, like the power.
Exactly. That's right on. So in the real world, I don't have an endless amount of power, right? It's not like in the simulator where I can just use, I don't know, this is ridiculous, but 1 million newtons of meters of torque, right? in the real world, my battery runs out of power, I don't have enough powerful motors, et cetera, whatnot. So I want to figure out the most efficient way, right, that I can get from P0 to Pn while using the least amount of power, right? So if we're thinking about autonomous vehicles, fuel, you don't have an endless amount of fuel. But yeah, that was the right answer. And so that's why it makes sense for us to minimize U. So we're not just randomly doing this. We have a reason as to why we're doing this. And this is why this makes sense. Cool. Any questions so far? No? Cool, awesome. So the first thing we're going to do, I haven't run anything, have I? Let's actually start running. So the first thing that we're going to do is we're going to define our equations of motion, B and A, display that again. And then we're going to save our P0 and our Pn, where n is equal to 20. So now here comes the next question. I need to define what my S and M matrices are. What is my S matrix? Yes?
Pn minus A to the n times P0?
Not my S matrix by itself. You're giving me my A matrix in the underdetermined form, but what is exactly. Where's your little carrot thing? No, over 6. Great. Thank you, guys. You would think I would know this. So here's the next question. How would I define my M matrix? Yes, you have a question? Or do you have an answer? You have an answer. Okay, great. Exactly. So how can I efficiently code that, right? Because I mean, I could hard code it in, right? And just say A19, B, A18, etc. But what if my n is 100? What if my n is 200? What do I do? Huh? Use a loop? Exactly. But how would I use a loop?
You can initialize like a matrix before and then just add on to it.
Yeah, that could work, yeah. Do you have another take on it?
No, I was going to say something. Just doing, iterate through 1 to n minus 1 do each time to compute a step, make sure that whatever came before goes after, because I want 1 to n instead of n minus 1, or 1 to n minus 1.
That's a good point. That's a good point. Make sure that the order that you're putting things in remains consistent. Is there another way that people have for doing this? I'll show you all what my way is. Oh, yes. So the answer was to do this in a for loop and to do it in such a way that you start in the backwards order, right? That's what you guys said. You start with A n minus 1 times B, but at the same time you want to be careful that the order that you're putting in these matrices is retained, right? Cool. Any other takes on that? There's so many different ways to code, right? And each way is unique, but I'll show y'all how I did this. Cool? Awesome. So, where is it? Cool. So, I have my little cheat sheet here. So the first thing I'm going to do is I am going to define an empty matrix. Are y'all familiar with this? Yes, go ahead.
What's the difference between doing that Julia and just having square and open and close square bracket?
So the difference between this is I'm telling it right here. I'm telling it in particular that I want an empty 2 by 0 matrix. Can you even do the open? Yeah, so you can do that. So when you do that, it does.
It does the same thing, but it will still have have a dimension. It wouldn't be like a zero dimension. So you might have issues with finding
Exactly. So, I mean, if you know what dimension your matrix should be, I would just advise that you sort of use this sort of method here. That was a good question. Also, I'm also still learning Julia, so. Okay, so we're gonna define a for loop. And I'm going to say, all right, does this make sense? It takes a minute, and I can go over exactly what this is doing.
Wouldn't it be n minus 1?
No. Hold on. No, because I start off with A1. Oh yeah, you're right. It would be n minus 1, yeah. Let's see. Cool. This doesn't make any sense, right? Here, I will explain what's going on. Okay, so what I have is, I told you that I have a for loop. Are we running? We're almost out of time. Right? So what happens when my k is equal to 1? Initially, I'm sorry? Yeah. Yeah, so when my k is equal to 1, my m will just be equal to b, because I define my m as just being an empty matrix. Remember, I define it as 2 by 0. So when my k is equal to 2, I have something that looks like this. Well, my m is equal to b, and this means that I get ab times b, right? When my k is equal to 3, again, this gives me a squared b, ab, b. Is this starting to make sense a little bit? You just have to sit down and just write it down and just see how this gets multiplied with each other. Yes?
When I